So presentations are not needed. Well, let's start from where I started. I started like 1.5 years ago, like asking myself, like I've seen this on Twitter, like BPF, yay, what's this thing? And so I decided to like dig a bit more. Then I joined Influx, and I had some time to do that. And in the meanwhile, I was asking myself, hey, how can I use this in Kubernetes? So after some time digging, I ended up using it in Kubernetes and everything. And so I decided to do this talk. This talk has been already presented at KubeCon North America and will be presented at the FOSDEM if anyone is there, and will be presented at the Velocity in San Jose in next June. So it's been quite interesting for committees to listen to this talk. And here, because Gianluca told me, you have to go there or I will beat you in your face. So I decided to go. I'm joking. So, like, in computer science, we like to create acronyms. So there's a new one, and new one. Well, BPF is a very old acronym. It started like with Unix initially. It's a Unix syscall, very well known that by historical reasons is Berkeley packet filter. So one could say, hey, this is just for network stuff. But we added an E as a prefix. So it's extended, then this means can do everything. So it can do everything. And extended Berkeley packet filters are specific for Linux, so you will not find extended Berkeley packet filters like in macOS or Solaris or whatever. But if you look at, like, if you have a Mac with you, you will find the BPF syscall in your Mac, but it's just for networking. So what is this BPF thing? I like to say that BPF is a tracing framework because BPF can be used as a front end for Linux tracing frameworks, like I will explain that later, uprobes, keyprobes. We will see what those terms mean. But actually, BPF can be used for a lot of other purposes. The main idea is that you have a way to go and tell the kernel, I want to execute this code in kernel space, and the kernel executes that code. This presentation is focused on how to use that code to get out metrics from the kernel, and to get out metrics from the kernel and aggregate them while using BPFs in a Kubernetes cluster. There's a postscript on there. There's another thing that's built on top of BPF that's called XDP, Express Data Path, that can be used to basically mingle with packets. So you can essentially say, I have this packet that's coming to this network interface, and even before that the packet reaches the kernel, you can read the packet and like drop it or allow it or do whatever you want, like send it to another CPU instead, these kind of things. But it's not the purpose of this tool. So I said that there are a lot of backends for tracing in the Linux kernel. We will see a bit more what BPF strictly means because there's a virtual machine and an instruction set that we'll see later in this presentation. But the important thing is that in the kernel, there are a few ways to actually extract traces from it and informations. And that part is not BPF. BPF is the medium you use to go there and take those informations, right? So like if you write a kernel module instead, you can go there and get those information in the same way, but you have to write and maintain a kernel module, right? So the first thing you eat when you talk about the BPF is the static trace points. There are actually trace points that are already there in the kernel, implemented in the kernel. And you can find them in this folder. Basically, like you ls that folder and you see all the trace points that kernel you are in is compiled with. Those trace points are basically trace points in the kernel that expose the information for that specific trace point. But the interesting things are the dynamic trace points. So you can basically write your trace points in the kernel in two ways. Or you go in a specific, like let's say that you have a program that has a function called getName, and it returns a string with a name, or a child pointer, whatever you have as a language. You can put a dynamic trace point in your program using a new probe that stands for user probes, and say in this binary, when this function is called, give me the return value. So you get the return value of that. What can go wrong? Like OpenSSL, give me the key, these kind of things. You can do that, but you need to be root, right? And key probes, the same thing, but for kernel functions, because kernel is a bit different, like you don't have a binary to go and everything. So you can basically, with key probes, get the output or the arguments, the stack trace of every function in the Linux kernel. And then there's XCP, that's autoscope. So the main idea is that you aggregate events at kernel side, and you just deal with a few of them in user space. Because when you create like your BPF program, you can, like let's say that you want to receive, every time a packet is received, you want to see, hey, a packet has been received, you want to count it, for example, like how many packets in an hour. It's better to actually count them in the kernel and just send like every hour the count of the last hour, this kind of thing. Instead of receiving like, let's say you are receiving like 50 million packets a second. It's going to be overwhelming for your monitoring system to receive 50 million requests every second, right? So that's the life cycle that happens when you load an eBPF program. So the first thing you have to understand is that like when you normally write a program, what happens is that like with compiled programs, you compile your programs for an architecture, and then you execute that program on that architecture, right? BPF programs are programs compiled for an architecture, but that architecture is not like your x86, 64 architecture that you have in your machine, but is the Linux kernel BPF virtual machine architecture that has a specific instruction set to allow the execution of BPF programs. That architecture is executed by the kernel virtual machine here, but before being executed is passed through a static verifier that analyzes the program and understands if that program can actually harm the machine. So like you cannot like kernel panic this machine with an BPF program. So the idea is that you have a user program that generates BPF bytecode by compiling it, or that has the BPF bytecode in a variable or whatever, that calls the BPF syscall to load your program with this BPF prog load. Then the kernel receives it, passed to the static verifier. Then the BPF engine understands what you want to do, like it's a uprobe, go to the function in my program and get the output, or it's a key probe, go to the function in the kernel and get the output, or it's a socket filter or whatever. And then that thing can just be finished there, like you can just write your logic there and it's okay. Or you can, maybe you want back the results in user space, like you wanted to extract something, so you want the results back. There's an asynchronous mechanism called BPF maps that you can hook into and receive back the results, right? There are a lot of different, like the hash maps, arrays. You can implement your own. And then you look up the elements in your user space program. So basically, you load the program there, and then you get back the information. The program that loads and the program that gets back the information doesn't have to be the same. Like, there can be a program that like loads 100 of them, and then a program that just scrapes the results. An important thing, BPF programs cannot be Turing complete right now. So like if you need to create a loop, for example, you cannot just do that. you will have to unroll the loop. Like if you are compiling the program here, and you want to like you have a list and you want to loop that list, and like it contains all the ports you want to scrape, you have to unroll that loop at compile time so that the BPF bytecode receives the actual expanded code. So you cannot just do that. Great source in any Linux machine is Manchu BPF that contains basically every information that you can find. And that was just an introduction. I mean, not everyone that uses the BPF should really be aware of that. Like, it's an implementation detail. Like, you are not aware of how your x86 architecture works. But you write programs for that, right? So there's an higher level. And in today's world, you're already using BPF programs when you use like your day-to-day tools. Like who use TCP Dump here? No one? Someone uses it? Cool. So TCP Dump at some point just switched to BPFs. And basically, when you use TCP Dump, if you add the -d argument, you can see the BPF assembly that's produced to run that filter. So, like in this case, I'm just saying this is the PCAP format, IP and TCP port 80. So I want all the IP packets, and this dumps out this instruction that says, is this an Ethernet IPv4 packet? Then you say, and TCP on port 80. So these things means, like, since I didn't specify source or destination here, this is going to assume source and destination. So this is filtering on source and destination for port 80 with this instruction here. So you're probably not aware, but you're already using BPF programs in your machines. Like, another important tool that, like, if you use, who uses containers here? Kubernetes, containers, whatever. Yes. So one of the main medium of isolation for containers is seccomp. That basically allows you to filter syscalls. That's why we say that containers are not sandboxes, is because the actual syscalls are in the target kernel. Like when you use gvisor, not to be confused with IOvisor, that it's an BPF thing. Gvisor is a container runtime that basically adds a layer that is an emulated kernel. Basically, I call it like that. And in that case, it's sandboxed. In this case, like with normal container runtimes, it's not sandboxes. So you have to actually have a way to filter the syscall you allow for your containers. Like, you don't want your container to be capnet admin. That means basically administer the network and the machine by inheritance. So you need seccomp for your containers. And seccomp actually has, in seccomp, you can load the BPF programs to filter the syscalls. So you can use the BPF VM actually to embed filters in your programs, like how TCP Dump and seccomp does. This example here actually works. So the idea is that, like, you can write the BPF programs in many different ways. The way we show you is with an higher level language that's called BPF Trace, but there are a lot of different ways to that. Like, you can write a C program that gets compiled to BPF bytecode. You can write the actual assembly directly, like I'm doing here with some macros. Or you can write, like, an idea I had. In Influx, we have a language that's called Flux. I want to actually create an intermediate representation for LLVM that it's compiled from Flux. So basically, it's just an assembly format and a set of instructions, so you can use, like, as any other language, whatever you want. In this case, I'm writing the instruction directly here. I don't remember what the instruction do, but the idea is that I'm loading this filter, and at some point with this filter, I can filter the permissions And basically, when at this point, basically I'm filtering ePerm. So after I install ePerm, I should not be able to write anymore. So when I try to write here, this thing just say me, hey, you're not allowed to write. So if you load these in your containers, for example, you can load actually this second program instead of like the main second. You basically can like just filter writes. Well, this is not a real use case because with sencomp you can already filter writes directly with the syscall. But if here I wanted to add like my specific logic, I could, right? So I can, like instead of filtering, I can send myself, hey, someone tried to write on like a database or whatever. These kind of things. You have a way to hook in second. More practical examples. A few of them. Like you can trace file open by file name. Trace queries done in a database. Like I said, you can create uprobes. Your database, when it executes a query, calls a function. So you can load uprobe on that function and get the query and just write the query to another database, right? Or you can trace TCP retransmission. Maybe not everyone is aware that one of the main issues with networks is in Linux is the TCP retransmissions, because Linux has a strange way of doing the retransmissions when it thinks that it's not able to handle the traffic, so it retransmits the traffic. And that's one of the things that not everyone monitors, but when you start monitoring it, you understand a lot of like, okay, I understood why the latency was high, these kind of things. And like also silly things like trace all commands during a bash shell, because bash calls readline is a function, and readline receives every command you write in the bash, so you receive the program. Trace block device I/O latency over time. This is one of the other interesting things, like tracing the block device I/O and tracing file opens by file name, because like if I would ask you, like if you were working with me, right, and one of the tasks is give me, for every file that we write or read, give me the I/O that operation uses and how many bytes are written over like in a specific range of time. These kind of things seems very simple, but when you try to do that, like you have a machine and you just have the Unix command, it seems like impossible. And even like with IO Trace or IO Top, these kind of programs there, it's almost impossible to achieve. So that's one of the things to think about, right? Or like you want to trace JVM events or Go runtime events, or you want to create a firewall yourself. Why not? Seems a straightforward task to do. And yes, even higher level APIs are there, like so that everyone can use it. One of the higher level APIs I like most is Go BPF, because I'm mainly a Go programmer, but also because I think it's interesting, the model that it uses. Go BPF mainly allows you to do two things. It allows you to compile a BPF program using Go. It uses Clang, but it's in Go, like you write Go and then it uses Clang. And the other thing that it does is that it loads a program and gives you Go primitives to actually use the maps and get back the information, right? One of the way I like to use this is that I compile my program before and then just load it, because the Go runtime becomes much easier because you don't need like Clang. Like you don't want a Docker image with like gigabyte of Clang and these kind of things. So I just compile the program before and I load it. But in this example here, maybe it's a bit small, but the slides will be made public. this line here, you have, you can zoom. No, you can't. No, I can't. Sorry. So I basically do a read file here, and I read the bash read line C. This program basically dumps out all the bash commands, the thing I said before. And then I load the uprobe here with this get return value function that is basically this function here. And then I attach, so I load the probe, and then I attach it to a binary on a function. And the binary is bin bash, and the function is readline. So basically, every time readline is called, I receive on this Go channel. I say that Go has a very interesting concurrency model, so it allows you to have channels and then consume the channels in Go routines, that are basically like threads. And then you can basically process the information. So the interesting thing is that you receive all those in the channel, and then you process the channel. And basically what happens here is that it does some verifications, and then it extracts the current PID from the kernel with this function, and then it reads the output of the readline function. And then with this perf submit, it submits that in the map that's been created here. And then I read those with this readline events map here. That's the same here. So I get the output and information. But like if you are just starting, a more interesting thing is BPF Trace. BPF Trace is a language that has been made it's like a domain-specific language for BPFs. So it has a syntax that like basically it's like made so that you can like immediately understand what you want to do. And like this program here is very similar to this program here, but here is like 100 lines plus the C, where it's like 2 lines because all the boilerplate is managed by BPF Trace. And this BPF Trace basically takes the BPF Trace program you wrote here and compiles it to the intermediate representation in LLVM. LLVM has a backend called BPF, so like when you compile something with LLVM, you can compile it for your architecture or for whatever, or for BPF. So it creates the assembly, BPF assembly directly. So they just had to write an LLVM front end, and then LLVM handles the compilation. And let's take this example here. Remember static trace points and everything. In this case, I'm using a static trace points on the syscalls, and then I'm getting every time sys enter read, that is a syscall, is called, I basically use the task, I create a map. This is the definition of a map. And I create a map with the task ID and the nanoseconds used for that specific task. And then I do the same thing for sys exit read. We will see more programs, and we will execute one later. And basically what happens is that I just do BPF Trace read BT, that is the name I gave to the program, and then I let it run for like 2 hours, and then I do Control-C that sends a signal to count the output, and it gives me this histogram, right? So BPF Trace is a quite complex tool. In the repo github.com iovisor/BPF Trace, there's an extensive walkthrough on how to write programs. It's a syntax very similar to C. You can like include Linux headers. You can create structs, these kind of things. But what you really want is to understand where you are looking, right? So this basically shows like all the different arguments you can use here, like trace point syscall here should be somewhere here, somewhere here, and like if you want to create a key probe, you will write key probe here, and then hold your specific key probe. This says just key probes are in this space, kernel space, uprobes are in this space, and in the user space you have the application space, you have the system library space, so you can load the eBPF program on a binary or on like a shared object library, right? And in the kernel, you can load BPF programs on the virtual file system. That is basically the abstraction that the kernel uses for dealing with files, or on like whatever you have on Linux. At some point, it will use the virtual file system, like even if you have LLVM, whatever, all those are managed through the virtual file system. Or if you are dealing with packets, you have access to the socket network buffers, these kind of things. But still, I can install BPF Trace on all the machines, like 500 Kubernetes nodes filled by SSH in every machine, and execute the BPF Trace. And if I want, like, if I want to instrument a specific pod that has an application, like to get information from that application, should I, like, before understand what the application is, install BPF Trace, these kind of things? 5 or 10 minutes? Okay. And these kind of things. So with Leo there, the only person in the first line, we made a tool that's a QCTL plugin that's called QCTL Trace. That basically is BPF Trace for Kubernetes clusters. In reality, it uses BPF Trace directly, but it deals with the fact that it goes in your cluster, loads the program there, and it gives you better results where you have the QCTL. We will see that. Then, at some point, like while doing it, things were getting more and more interesting for Uvisor, that is the Linux Foundation entity that makes BPF programs, like the BPF project for the Linux Foundation. And so we decided to donate it to Uvisor. And Brendan Gregg, that is working on Netflix on performance, made a tweet about that. And it was very popular. And so QCTL Trace. QCTL Trace has basically the same syntax of BPF Trace, plus the fact that it deals with Kubernetes clusters. So in this case, I'm saying QCTL Trace. I think that for those that doesn't know, QCTL plugins are basically binary programs or programs that have the name QCTL dash whatever you want. So when you create like QCTL Trace in the repo is QCTL dash trace, it's compiled as QCTL dash trace, but the QCTL understands that from your path. So when you run QCTL space trace, it seems integrated. So if you want to write your own, no. The only caveat, and Leo helped me a lot with that, is that it doesn't give you all the things for free. Like you don't have like a way to filter namespace and these kind of things. So you have to basically implement the QCTL Trace main command line, but I didn't do that. He did that. When I started the project, I didn't do that, and it was very like clunky. Like it didn't work as expected, but now it does. So QCTL Trace run, and then with E, you pass an inline program, or you can pass a program with -f with loads from the file. And this program here loads a key probe on these. A key probe is you attach your BPF program to a function in the kernel. So I found this do sys open function that basically means every time a file descriptor is open, and then I print the name of the file descriptor here. And that program is loaded on this node only, so only on that node, or you can do pod / and load that on that pod, on the pod. And then I attach a TTI so that I see immediately the results. this is the same thing, but I load the program from a file, and this program doesn't give, like the program before was giving you a stream of results, so like you can create a CSV or whatever, while in this program here I use a function that plots an histogram that called the hist function. So you, it waits for Control C and plots the histogram. As I said, you can have a stream of results. So, like, if you use the printf function in a clever way and you output a CSV, you can pipe that with like tools, with terminal visualization tools like VisiData in this case, and you plot an histogram with VisiData or whatever. Or you can create a CSV file and load it in Excel. And there's the demo. Sit down. Oh, the microphone is on the table. No worries. I'm loud enough. Okay. So I have an application running called Caturday. Isn't this fun enough? That shows you cats and a counter and information on your machine. And this is a very cloud native app because it has Prometheus endpoint. But Prometheus endpoints are not enough for me. I want to get the counter with the BPF program because I can. So I will do that, and I have this one-liner txt file. Where does my program here? QCTL Trace run. I attach a URAT probe. I didn't say that. URAT probes are basically U probes, but in those you have a function that's called ret. Basically, you can get the return value of the function. And in BPF Trace, because this is still BPF Trace, you have a function called, you have a variable called retval. That is the return value is not actually directly typed, but since it's a radian integer, I didn't have to cast it. So even if it's a string, it's an integer, then you have to convert the integer to a string. Or if you can like receive the address of a pointer, if you go to the pointer and get the value. So I will load these. Oh, there's no pod. QCTL get pods. And then I take one of the pods. And I load it, and basically the trace is already there. Trace get all namespaces, show me that I have a trace on the local node. My Kubernetes cluster is local, so I don't have to go anywhere. And the trace is this one. I have a lot of other commands like logs. I can take the logs and everything, but I want to show you the output here. So I have this thing running, and I have some cats, and I reload the page. There's the counter. I reload the page. The counter again. How this is made? Basically, you see here that the URAT probe is everything in Linux is a file. So even your binary is a file somewhere in your system. So even if the BPF trace, in this case, pod, because I schedule, when I run this, I schedule trivia, so I'm almost in time. When I schedule your BPF Trace program, I created a job that starts a pod, the right machine near to your pod that can go there and take information, but I don't enter your namespace. I'm from the outside because I didn't want to mess with people clusters. But since I have the PIDs, I can go there and take the binary you're running, right? And BPF QCTL Trace in this case exposes a container PID variable that you can use to filter the file, to filter the process ID, and then use that in the proc file system to get the actual executable of the pod. This support is a bit, this pod support is a bit clunky now because there's an issue in BPF Trace that they have to fix to add namespace and support, but it's not there yet, so you have to do this for now. And then, so basically this is the Caturday binary, and on that binary I have this variable that is incremented every time. Is like an atomic variable that's incremented. And I just, no, sorry, this is not an atomic variable, this is the function, sorry. So every time the function is called, I get the return value here, and I have the PID, and I dump it out. So to prove that, yes, Caturday is mine. Yes, there are cats everywhere. And counter value is just this. So I'm just looking to this function that is in Go, and Go, it was written main counter value because in the main packages it was like in a package under like github.com, my super username, my package, it would have been github.com, my super username, my package, whatever, dot your function. And let's see some other examples. One-liner. Let's see if this works still. So in this BPF Trace program, I have some includes from the kernel because I need to access some kernel structs. And this basically adds a key probe on VFS write. So every time a file is written, every file ever, and I take the file name and I just print an histogram with the sum of the bytes written. No, in this case, I just print the bytes of the file the sum of the bytes written, and in this one, I print the histogram with this ist function. So I just use a different function. I have finished my time, sorry. So in this case, I'm running this other one, and then I'm using, okay, this cluster is running locally on my Docker daemon, so I can just do stupid stuff here, or hello, do things in my kernel, and when I do Control-C, it shows me an histogram of every single file written. So Kuba proxy log, storage ASTMP, what the hell is that? score adjust, interesting. Cookies. The cookies file is writing everything, and even like it's not just file. Everything in Linux is a file. So every file descriptor I see here, Unix file descriptor, TCP. So this is basically the amount of TCP bytes written in the window of time, and since it's an histogram with different, like it will show you the different chunks of bytes written, so it will divide them. And I can see here, basically, that most of my TCP calls are behind 16 and 32 bytes. That makes perfect sense. And everything. So like, let's say that you have an application, like this is, I wrote this thing for, I ran out of time, you're laughing? A bit, sorry. I will finish soon. Let's say like in Influx we have a storage layer that writes a lot of bytes on disk, And we didn't really have a way to understand like when that is writing, it's writing a gigabyte altogether, or it's writing chunks of 20 kilobytes or whatever. So with this thing, we see the distribution and we can optimize for different kind of file systems. So any BPF book recommended? There's no BPF book right now. Jess and David, Jesse Frizzell and David Covey are writing a book I'm reviewing about this topic. So let's see if that happens. And if you need any, there's still the Cubicon logo, sorry, Gianluca. If you need any reference, I recommend you to read the samples BPF folder in the Linux kernel. I recommend you to read the Cilium documentation. Cilium is a network plugin for Kubernetes that is using BPF. That I consider basically the documentation for BPF, because in their documentation there's everything. And there are a lot of blog posts, and BPF Trace gives you a lot of interesting insights, and the links are there if you want to see them. And thank you. I register a domain, bpf.sh. If you want an alias there, just drop me an email. And thank you.